Inductive reactance is indeed more problematic in steel raceways, leading to increased impedance. Inductive reactance, often denoted as XL, signifies the opposition to alternating current flow due to a circuit's inductance. Inductance itself is the property within a circuit that resists changes in current. Steel, being a magnetic material, readily magnetizes when exposed to electric current. When alternating current flows through a steel raceway, the raceway becomes magnetized, generating a magnetic field. This magnetic field, in turn, induces an electromotive force, or EMF, within the circuit which opposes the current flow. This opposition manifests as inductive reactance. Conversely, aluminum is a non-magnetic material. This means it does not magnetize when exposed to electric current. Consequently, when alternating current passes through an aluminum raceway, the raceway doesn't generate a magnetic field, and therefore, no EMF is induced within the circuit. As a result, the impedance of a circuit is greater when installed in an aluminum raceway and less when installed in a steel raceway. To further elaborate, consider the underlying principles of electromagnetism. When current flows through a conductor, it generates a magnetic field around that conductor. The strength of this magnetic field is directly proportional to the magnitude of the current. In alternating current circuits, the current is constantly changing direction and magnitude, leading to a fluctuating magnetic field. When this fluctuating magnetic field interacts with a nearby conductive material, it induces a voltage in that material. This phenomenon is known as electromagnetic induction. In the case of steel conduit, the magnetic field generated by the current-carrying conductors within the conduit induces eddy currents within the steel itself. These eddy currents circulate within the steel and create their own magnetic fields, which oppose the original magnetic field produced by the conductors. This opposition increases the overall impedance of the circuit. The amount of inductive reactance depends on several factors. Firstly, the frequency of the alternating current. Higher frequencies result in greater inductive reactance. Secondly, the inductance of the circuit. Greater inductance also leads to greater inductive reactance. Thirdly, the permeability of the surrounding material. Materials with higher permeability, like steel, increase inductive reactance. Aluminum, being non-magnetic, does not exhibit this effect to a significant extent. The geometry of the conductors and the raceway also plays a role. The closer the conductors are to the raceway, and the greater the surface area of the raceway, the more pronounced the inductive reactance effect will be. In practical applications, the increased impedance due to inductive reactance in steel conduit can lead to several consequences. Firstly, voltage drop. The increased impedance causes a greater voltage drop along the length of the circuit. Secondly, increased heating. The eddy currents induced in the steel conduit dissipate energy in the form of heat, which can lead to overheating and potential damage to the insulation of the conductors. Thirdly, reduced efficiency. The increased impedance reduces the overall efficiency of the circuit, as more energy is lost in the form of heat. To mitigate the effects of inductive reactance in steel conduit, several measures can be taken. Firstly, use aluminum conduit. Aluminum conduit is non-magnetic and does not induce eddy currents, thus minimizing inductive reactance. Secondly, use larger conductors. Larger conductors have lower resistance, which helps to offset the increased impedance due to inductive reactance. Thirdly, space the conductors further apart. Increasing the distance between the conductors reduces the magnetic field interaction with the conduit. Fourthly, use non-metallic conduit. Non-metallic conduit is non-conductive and does not allow eddy currents to flow, thus eliminating inductive reactance. The choice of conduit material depends on several factors, including the application, the environment, and the budget. Steel conduit is generally stronger and more durable than aluminum conduit, making it suitable for harsh environments where mechanical protection is required. However, aluminum conduit is lighter and easier to work with, and it offers better corrosion resistance. Non-metallic conduit is the least expensive option, but it is not as strong or durable as steel or aluminum conduit. In summary, the key difference between steel and aluminum conduit lies in their magnetic properties. Steel, being magnetic, induces eddy currents and increases inductive reactance, leading to higher impedance. Aluminum, being non-magnetic, does not exhibit this effect to a significant extent, resulting in lower impedance. The choice of conduit material should be based on the careful consideration of the application requirements and the potential impact of inductive reactance. It's important to consult the National Electrical Code, or NEC, for specific requirements and recommendations regarding conduit selection and installation. The NEC provides guidelines for minimizing inductive reactance and ensuring the safe and efficient operation of electrical systems. For instance, NEC Section 300.3 C1 requires that all circuit conductors be installed in the same raceway or cable. This helps to minimize inductive reactance by ensuring that the magnetic fields produced by the different conductors cancel each other out. Additionally, NEC Section 310.15 B3 addresses the ampacity deriving of conductors in raceways. When multiple conductors are installed in the same raceway, their ampacity must be derivated to account for the increased heating caused by inductive reactance. The specific derivating factors are provided in NEC Table 310.15 B3. Furthermore, NEC Chapter 9 Table 9 provides impedance values for various types of conduits, including steel and aluminum. These values can be used to calculate the voltage drop and other performance characteristics of electrical circuits. It's essential to consult these tables when designing and installing electrical systems to ensure that the conductors and raceways are properly sized and configured. In addition to the NEC, other industry standards and best practices can also help to minimize inductive reactance. For example, it's recommended to use low reactance cables and connectors whenever possible. Low reactance cables are designed to minimize the inductance of the circuit, which reduces inductive reactance. Similarly, low reactance connectors are designed to minimize the impedance at the connection points. Another best practice is to use bonding jumpers to connect the conduit to the grounding system. Bonding jumpers provide a low impedance path for fault currents, which helps to reduce the voltage drop and improve the safety of the electrical system. The size and type of bonding jumper should be selected based on the size of the conduit and the available fault current. Proper installation techniques are also crucial for minimizing inductive reactance. For example, it's important to avoid sharp bends in the conduit, as these can increase the inductance of the circuit. It's also important to ensure that the conduit is properly supported and secured to prevent it from vibrating or moving. Vibration and movement can cause the conductors to rub against the conduit, which can damage the insulation and increase the risk of electrical faults. In conclusion, inductive reactance is an important consideration in electrical system design and installation. Steel conduit can significantly increase inductive reactance due to its magnetic properties, while aluminum conduit has a minimal effect. By understanding the principles of inductive reactance and following the guidelines and recommendations of the NEC and other industry standards, engineers and electricians can minimize the impact of inductive reactance and ensure the safe and efficient operation of electrical systems. Remember to always consult with qualified professionals and adhere to all applicable codes and regulations when working with electrical systems. The increased impedance in aluminum is due to the skin effect. At higher frequencies, alternating current tends to flow along the surface of a conductor rather than through the entire cross-sectional area. This phenomenon is known as the skin effect. The skin effect is more pronounced in materials with higher conductivity, such as aluminum. As a result, the effective cross-sectional area of the conductor is reduced, which increases the resistance and impedance of the circuit. In steel conduit, the skin effect is less pronounced due to the lower conductivity of steel. However, the magnetic properties of steel have a much greater impact on the impedance of the circuit, as discussed earlier. Therefore, the overall impedance is lower in steel conduit compared to aluminum conduit, despite the skin effect. It's important to note that the skin effect is frequency dependent. At lower frequencies, the skin effect is less significant and the difference in impedance between steel and aluminum conduit is smaller. However, at higher frequencies, the skin effect becomes more pronounced and the difference in impedance becomes larger. The frequency at which the skin effect becomes significant depends on the conductivity of the material and the diameter of the conductor. For typical electrical wiring applications, the skin effect is generally not a major concern at frequencies of 60 Hz or lower. However, at higher frequencies, such as those used in radio frequency or microwave applications, the skin effect can become a significant factor. In these cases, special conductors and raceways are often used to minimize the skin effect and reduce impedance. These conductors may be made of materials with lower conductivity or may have a special geometry that increases the surface area of the conductor. The raceways may be designed with features that minimize the magnetic field interaction with the conductor. In addition to the skin effect and inductive reactance, other factors can also affect the impedance of electrical circuits. These factors include the resistance of the conductors, the capacitance between the conductors, and the presence of any inductive or capacitive loads in the circuit. The resistance of the conductors depends on the material of the conductor, the length of the conductor, and the cross-sectional area of the conductor. The capacitance between the conductors depends on the distance between the conductors, the dielectric constant of the insulating material between the conductors, and the surface area of the conductors. Inductive loads such as motors and transformers introduce inductive reactance into the circuit, which increases the impedance. Capacitive loads such as capacitors and fluorescent lights introduce capacitive reactance into the circuit, which decreases the impedance. To accurately calculate the impedance of an electrical circuit, it's necessary to take all of these factors into account. Complex calculations may be required, especially for circuits with multiple loads and complex geometries. Fortunately, there are many software tools and calculators available that can simplify the process of calculating impedance. These tools can take into account all of the relevant factors and provide accurate results. In addition to calculating the impedance of an electrical circuit, it's also important to measure the impedance in the field. This can be done using a variety of instruments, such as impedance analyzers and network analyzers. These instruments can measure the impedance of the circuit at different frequencies and provide valuable information about the performance of the circuit. Impedance measurements can be used to identify problems such as loose connections, damaged insulation, and faulty components. They can also be used to verify that the circuit is operating within its design specifications. In conclusion, the impedance of an electrical circuit is a complex property that depends on a variety of factors. Steel and aluminum conduit have different effects on the impedance of the circuit due to their different magnetic properties and conductivities. It's important to understand these effects and take them into account when designing and installing electrical systems. By following the guidelines and recommendations of the NEC and other industry standards, engineers and electricians can minimize the impact of impedance and ensure the safe and efficient operation of electrical systems. Remember to always consult with qualified professionals and adhere to all applicable codes and regulations when working with electrical systems. The NEC references impedance in sections related to voltage drop calculations, short circuit current calculations, and grounding and bonding requirements. For example, section 250.4 A5 requires that the impedance of the grounding path be low enough to facilitate the operation of overcurrent devices in the event of a ground fault. This ensures that the fault current is quickly interrupted, minimizing the risk of electric shock or fire. The impedance of the grounding path is affected by the size and material of the grounding conductors, the length of the grounding conductors, and the connections between the grounding conductors and the equipment. Proper grounding and bonding techniques are essential for minimizing the impedance of the grounding path and ensuring the safety of the electrical system. Another example is in voltage drop calculations. The NEC recommends that the voltage drop in branch circuits and feeders not exceed 3% and 5% respectively. Excessive voltage drop can cause equipment to malfunction or overheat. The voltage drop in a circuit is directly proportional to the impedance of the circuit. Therefore, it's important to calculate the impedance of the circuit accurately when performing voltage drop calculations. The impedance of the circuit is affected by the resistance and reactance of the conductors, the length of the conductors, and the load current. Software tools can simplify the voltage drop calculation process. Short-circuit current calculations also rely on impedance values. The NEC requires that electrical equipment be rated to withstand the available short-circuit current at its terminals. The available short-circuit current is determined by the impedance of the electrical system upstream of the equipment. A lower impedance results in a higher short-circuit current. It's essential to perform short-circuit current calculations to ensure that electrical equipment is properly protected against overcurrents. The short-circuit current calculation process involves determining the impedance of the utility power source, the transformers, the conductors, and any other components in the electrical system. Specialized software programs are often used to perform these complex calculations. In summary, impedance is a fundamental concept in electrical engineering that plays a crucial role in various aspects of electrical system design and installation. Understanding the effects of steel and aluminum conduit on impedance, as well as the requirements of the NEC, is essential for ensuring the safety and efficiency of electrical systems. Always consult with qualified professionals and adhere to all applicable codes and regulations when working with electrical systems.